Let's take a look at problem number 41 on page 147 on your forces assignment and Newton's third law. Problem number 41 and 42 are identical except that we changed the masses. So if you understand one, you can certainly do the other. All right, so this is the system. It shows to draw a diagram of what we're given. A 2 kilogram mass and a 3 kilogram mass attached to a lightweight cord dangling over a frictionless pulley. And it says this is free to move, and we want to find the acceleration. All right, so this is a diagram of what we have. We have a pulley with these two unequal masses dangling from it. This is actually called for an Atwood's machine. And it was used by a British physicist in the 18th century to study acceleration. Okay, the massless cord and frictionless pulley is just saying those items are not a player. All that we're worried about are these two masses. Now, each one of these masses is going to have a force associated with it, the force of gravity. Now, I can see one, because it's more massive, it pulls harder on the system than the other one. This is what gives us our acceleration. And just by intuition, we can look at this and see that is what's going to happen. All right, what I want to do is let's just isolate the system. Let's get rid of the pulley, and we're kind of even getting rid of the cord. And I'm just looking at this as two blocks that are put together. It could be glued together, or they could be sewn together with this cord. It doesn't matter. Let's just look at it as a whole. As a whole, on this system, I've got two forces acting on them. All right, one is a 19.6 Newton force pulling it one way. The other is a 29.4 Newton force pulling it the other way. All right, obviously the 29.4 is bigger, so I have a net force not equal to 0. So it's going to accelerate to the left. We'll call that acceleration to the left. We'll call that our positive direction. It always works out well to use your direction of motion as positive. All right, we can use Newton's second law then. We have two forces, we have a mass. Let's compute the acceleration. Again, I'm using the direction of acceleration as positive. I don't have to. All right, I could use the other way. It really doesn't matter. But what I have is my net force is a subtraction of these two forces because they're going in opposite directions. And I'm using the entire mass of the system. I can compute acceleration of the system, which is what the problem asked me to do. Now I can use this acceleration, and let's go back and let's look at the tension in these cords. How are we going to do that? Well, the temptation when I look at tension is we have already learned that in a rope, a tension is going to be the same throughout the rope. All right, so it's easy to say, well, gee, the tension on the 2 kilogram mass is just going to be the weight of the 2 kilograms. And that the tension on the 3 kilogram mass is going to be due to the weight of the 3 kilogram mass. That's not correct. If we were in equilibrium, yes, but this system is accelerating. We've already determined the magnitude of the acceleration, and the 3 kilogram block is going to accelerate downward. Since they're connected, the 2 kilogram block is going to accelerate upward at the exact same rate. Okay, so in order for this to happen, let's look at the 2 kilogram block. I have a 19.6 newtons of weight. So if this is going to accelerate upward, the tension cannot be equal to its weight. It has to be greater than its weight in order to accelerate upwards. Let's look at this block. Its weight is 29.4. There's no way it can accelerate at 29.4 if the tension is 29.4. The tension must be less in order for the 3 kilogram block to accelerate downwards. So, we know that in order for, oh, Lord of mercy, let's get all this back. There we go. In order for the blocks to accelerate up and down, my force of tension has to be somewhere between these two values. Let's take a free body diagram of the system again, and this time I'm just going to look at the 2 kilogram mass. I could equally do this using the 3 kilogram mass. It's going to turn out exactly the same. What do I know about it? I know it's accelerating upward. I know its weight is 19.62, and I know the force of tension has to be greater than 19.62 if it's going to accelerate upward. Well, I have enough data here to go to Newton's second law. We know that the acceleration has been computed from the previous exercise. I'm going to call up the direction of my motion positive. Therefore, the tension is positive minus the weight, which is negative, is equal to my mass, 2 kilograms, times the acceleration that I've previously computed. So my only unknown is now force of tension. And I can use this exact same method on the next problem. It does the exact same thing. It's an Atwood's machine, just different masses.